So thanks a lot for coming to the colloquium of the first colloquium of 2024. Today we are very happy to have Brodie Popovic from Lyon, from the Institute des Infinis de Lyon. So he did his PhD at Duke University. He's an observational cosmologist working on supernovae. And today he's talking about supernova cosmology with the DES, the Dark Energy Survey. Please.
Thank you. Good to be here. So as was pointed out in the pre-presentation chatter, you may not recognize a lot of these faces on this photo, but there are some that you may. Got the old SNLS 5 or SNLS 3-year guy here, Mark Sullivan, and I mean, there's myself, Matt Smith, Annie Smoller here, was a postdoc at Clermont-Ferrand for a while. And so, you know, Rick Kessler here, infamous simulations guy, shockingly fluent in French, although he hides it really well. And a handful of other people from across the world. And so the big picture here was the 2022 Duke held DES Cosmology collaboration meeting. And, you know, obviously these are the people that couldn't make it. And this is really sort of where the final analysis crystallized and got completed and pushed out. And so what I'm going to be doing for the next however many times I have is kind of talking about the process, what we use Type 1a supernova for, the cosmologies we measured, and then at the very end, a little bit about kind of what we're looking forward to and what yet needs to be done. If you have any questions, please feel free to holler. Interrupt if there's something that's not clear. Same goes for y'all good folks on the Zoom. And I will not be seeing it, but I trust that it will be seen. So the Dark Energy Survey, DES as we call it in the States to avoid confusion with DESI or DESC, because this keeps tripping me up. But this ran for 5 years, from 2013 to 2018, across the southern sky in the GRIZ filters. You may recognize, not from this slide, but the infamous tank shape we've got, because the area of the sky has to cross over stripe 82 to match with SDSS, and that makes it look a bit like an Abrams tank. And so we launched with the overall goal of understanding dark energy, maybe not too surprising of a goal considering the name of the survey. I'm afraid to tell you we have failed. I don't know what it is. If you know what it is, please tell me. That'll make this presentation go a lot easier and a lot faster. All I can really tell you is it's about 70% of the universe. It's dark. And for the most part, current data agrees with a cosmological constant, lambda, which comports to our best known model of the universe, ΛCDM. And this was discovered in the late 90s, this being dark energy, with Type 1a supernova. And so it's probably worth talking a little bit about what Type 1a supernova are, how they're used, and how this matters to cosmology. So at the end of the game, what we need to do with Type 1a supernova, or really a lot of cosmological measurements, is we got to get a redshift and we've got to get a distance. That sounds easy. As it turns out, that's the hardest part of what we do. But if you have a redshift and a distance, and each of these little black points is, you know, a mock supernova, then you can fit a cosmology to these curves. So typically the way this has worked is that we have low redshift supernova and then high redshift supernova, because the methods of acquiring these are a little different. And when you put the two together, you get enough leverage to see a universe with matter only, which, as we learned in the 90s, was not the case. And you may not be surprised to know that the universe is not dark energy only. If it was, I don't think we'd be here right now having this discussion. But in general, what is dark energy? I don't know, but we can describe it with an equation of state parameter W. And this sort of boils down all we need to know about it to a single number. If we find that W is -1, we get that cosmological constant, we'll get ΛCDM. And if it's not -1, then it's something else, and the mystery deepens. And so supernova in particular as local distance measurements are really good at getting this dark energy and matter. So we can represent that in this matter density, dark energy density space, or as we do a bit more frequently and a bit more commonly in supernova, W versus omega matter. And so this provides a great complementary probe to things like CMB and BAO, such that when you combine our supernova results with those, you're going to get very precise measurements of W. So why type 1a supernova may be a good question, and that's because they are pretty standardized candles. The peak brightness in type 1a supernova, after several empirical corrections, and this is kind of where it gets thorny, but after that, it comes down to about 10% scatter. For context, that's going to be about 0.14 magnitudes, give or take. Before any standardization, it's about 0.4 magnitudes of scatter. For context, the signal of dark energy is about difference of 0.2 mags. So without proper standardization, we can't detect dark energy at all. And so, standardization is going to be really important to this process. If you're standardizing wrong or not standardizing enough, your signal is going to get buried in the noise. But despite this, they are still the best local distance measurements, and I think they're pretty interesting. So I've kind of alluded to these empirical corrections. We have an example of a whole bunch of different data points we've got. It is, your absolute magnitude or flux as a measure of time, where these data points are all data. And what we do is we use a light curve fitter to find the peak brightness and simultaneously apply these two corrections. This first correction here is called stretch. It's also referred to as X1, and it is basically related to how long the light curve takes to decay. And the second one is color C, and that is best understood as sort of an astronomical color, so the difference in flux between two bands. And after you apply those light curve corrections, you go from this kind of mess of noise and signal to a much cleaner, more homogeneous and more standardized group. And you can derive distances a lot better.
Why does the stretch matter if you're only interested in
because and I always get this one switched up because of the plus sign and the minus sign, but the supernova that take longer to degrade are intrinsically brighter than the ones that are shorter. Yeah, exactly.
So it takes longer to get up.
Yes. So to be honest, we don't really know. That's one of the tricky things, is that we still don't entirely understand the explosion model. I mean, I can tell you a white dwarf is involved, and that's about it. We don't know if there's two. But yes, there are some theories about how there might be more nickel content that then degrades longer, causing a longer light curve. And since there's more nickel, there's more energy in the initial peak. But when I say a lot of this is empirical, we are really only just now starting to incorporate like more astrophysical processes into our standardization. Is that good? I know that's not a terribly satisfying answer, but I do promise it is an active thing. Yeah. So this is sort of, with all of that being said, the rough overview of what a modern supernova cosmology survey looks like. We've got to take our data, combine it with simulations, do all of the analysis, and come to the cosmological results. And so most of the rest of this presentation will be going over each of these steps one by one, talking about the big kind of takeaways we have, who worked on it, who did what, that sort of thing. So obviously, can't really do analysis of data without data. So we are going to talk about that. And one of the things that makes DES unique relatively is that we are dropping a historical requirement of spectroscopic identification. And I'll talk about what that means in a little bit, because that's going to have some knock-on effects. But the important takeaway here is we get a lot of supernova. Historically, it's been about 200 supernova per survey. And we have about 1,500 all from the same telescope with a redshift range that is pretty darn good compared to Pantheon Plus, which is currently the most precise published measurement of dark energy with supernova. So as you can see, Pantheon Plus here is 17 different supernova surveys combined because of that spectroscopic requirement. And that becomes a bit of a nightmare wrangling 17 different telescopes, 17 different 0 points, 17 different calibration methods. And so switching to a single telescope where we have this all pretty well characterized is a huge relief. And so the people that really took charge of this are Dylan Brout, who is now a professor at Boston University, and Bruno Sanchez, who is currently working with the CPPM in Marseille. And they were in charge of doing all of the photometry and scene modeling and that lovely, awful stuff. Things that absolutely need to be done, but I have been assured are not terribly fun. So you may ask, how do we find these supernova? And despite what this picture may have you believe, it's not as easy as finding the red circle in the galaxy. You have to see the supernova, come back to the galaxy later on, then actually figure out what galaxy hosted the supernova. Sometimes it's not terribly clear. And the way we do this is if you look at all of your galaxies in the sky next to your supernova, say if the supernova occurred here, you can weigh the angular separation of the supernova and the galaxy by the orientation and size of the galaxy to then figure out the most likely host. An obvious question is, how good are you at identifying the host? The answer is pretty good, actually. Using simulations, we found about a 5% misassociation rate at the end of the day. And the actual impact on that is on W and our cosmological parameters is pretty negligible. This is largely due to if you get the redshift wrong, you usually get it really wrong. And then that's going to cause your outlier cuts to trigger, or if you just get it a little wrong, it'll increase the scatter by a little bit, but not too much. So luckily, supernova host identification, shockingly, not really a problem. So after you've isolated the supernova, you get all of your light curves. And so we have our normalized light curves in each of our bands, all shifted by redshift. And so this covers a range of, slight typo there, 0.1 to 1.13 in redshift, which is still a very good range, and it's the largest high redshift sample from a single telescope with about 1,600 supernova over the course of 5 years. And again, for reference, the DES 3-year result had 200 supernova. And this is not the difference in 2 years of observation. This is the difference of relaxing that spectroscopic requirement. So, simulations. I've been told that this is a bit of a contentious topic between the States and France. The United States loves to use simulations a lot. Not as much here. I'm going to at least try to make the case that it's not all bad. And so what do we do is we want to make sure our simulations match our data as best as possible. And this is largely done because we are going to have selection effects. At higher redshifts, your dimmer supernovae may not be observed. That's going to cause Malmquist bias. You want to fix for this. You can either chop a bunch of statistics to make sure that you go from a magnitude limited survey to a volume limited one, or you can start using simulations to see, like, if I have these simulated supernova that go off and we don't observe them, how does this affect our cosmology? How does this affect our distance measurements? Stuff like that. And the sign that you're doing a good job is that you put in some distribution of true parameters. You process them through all of the observing logs of your data, calculate how likely you are to see them. And if you still get really good agreement between your simulations and your data for your redshift, your peak brightness, and these two empirical standardization parameters, then you're doing a pretty good job. Because at the end of the day, these 4 histograms is really all of what our cosmology sees. However, we want to do better. So we are really working our butts off to try to get more host galaxy information in, more kind of astrophysical processes in. And so this is sort of the first time that we're really taking a close attention to like the host galaxy colors, because we know that that corresponds really well to the star formation rate. And there's a lot of information that we can draw from star formation rate, like how it might relate to the dust content of the galaxy or the likely progenitor stars. Can I help you? I'm seeing some confusion. Sorry. This is the part that trips everybody up. And it's only going to get a bit weirder from here. So that's the nice, simple overview version. And I was working on this along with the lead of the analysis and the guy that built SNe, which is the simulation software we use, Supernova Analysis at SNe. And so I have kind of referenced this a little bit, thrown in some hints and stuff, but our historic SN1A samples have required that live spectroscopic confirmation. This is expensive, extremely limiting. It cuts our sample size down by about a factor of 10, but it ensures that only type 1A supernova end up in our analysis. And this is really important because by eye, the light curves of a type 1A and any other type of supernova are fairly difficult to distinguish. I can't do it by eye. None of the grad students I've asked to do it by eye have been able to. So we're going to need to figure out a way to fix that. And this is especially important because a lot of the discussion around the Legacy Survey of Space and Time and the Nancy Grace Roman Space Telescope, which are going to be our next 2 really big surveys that capture SNE1A, these are going to be happening without a guaranteed live spectroscopic follow-up. So this means that we are going to have a boatload of statistics. For DES, it was about an increase of 10. For Roman and LSST, it looks like it'll be a sample size increase of 100 times. But we're going to have to tackle, like, how does this non-1A contamination affect our results? If you're trying to standardize things that just can't be standardized, is this going to cause biases? Is this going to increase our uncertainties? How is this going to affect us?
So the spectroscopic confirmation is the absence of certain emission lines.
Yes.
In the spectrum.
Type 1A have a silicon line that's very strong compared to other types of core collapse, 1B, C, type 2, et cetera, which don't have that silicon line. So if you have a spectrum, it's relatively easy to look and say this is a type 1A. And if you don't have a spectrum, it becomes a lot harder.
So here you have 4 or 5 colors. So does that allow you to reject the?
It's a very good question. We'll get to that actually. I have a whole couple slides dedicated to like how well we're doing at identifying non-1A supernova. The quick answer is some will creep in. I'll get to it.
Okay.
Yeah, it's a good question. It is a really important thing because if we can't handle this, then I don't know what we're going to do for LSST and Roman, but good question. So, hey, this is one of those slides. So there will be non-1A supernovae present in our sample. And so what we wanted to do this time was get a really good handle on our simulations of non-1A supernova. So in addition to 1As, we also went and we simulated type 2, type 2N, type 2B, 1B, 1C, 91BG, a whole bunch. And on top of that, we made sure to do a whole bunch of different models of simulated core collapse supernova. So we have like our normal one, we have de-reddened versions where we have removed the host reddening that we included. We have another one where we're changing the luminosity function, which is not terribly well constrained. And so this will shift the overall brightness. And then an entirely separate set of independently created non-1A supernova simulations. And what we have is the linear scale number of supernovae with the Hubble residuals. We'll talk a bit more about what the Hubble residuals mean, but it's basically the difference between the individual measurement of the supernova and the best fit cosmology. One of the things we're going to take advantage of is that core collapse supernova are expected to be intrinsically fainter than their 1A counterparts. So if you look, you should see that a lot of these Hubble residuals are focused around 1 rather than 0, and that's to be expected. You would expect your fainter contamination to show up as an extra shoulder in this. And this is just non-1A, and we'll see an example of what that non-1A contamination looks like compared to the 1A in a little bit. But I want to emphasize with this that like we are throwing everything we have at the wall here to make sure that we're characterizing this as best as possible. As many questions as you might have about how 1A go off, in what way, how bright they are, we've included those.
How many not 1A supernovas are in your sample?
And we've also done something similarly heinous for type 1A supernova. So what this is the results of a simultaneous fit of about 12 different model parameters. And what we've done is kind of, for the first time, we're taking a really rigorous approach to how our host galaxy environment affects our supernova. So if this looks complicated, it's because it is. But basically what we've done is we've said there exists some intrinsic distribution of supernova that as they go through the host galaxy dust, they get reddened and dim by the dust content. And we went and simultaneously fit all of that dust content with the intrinsic stuff, assuming different RV distributions and different E of B minus V distributions as a function of the mass of the host galaxy. And we got a whole bunch of results. We got all of the covariances between these results. And then we went and we included a whole bunch of systematics to make sure that we don't know how well we're constraining this. We're making sure we're propagating all of those uncertainties into our cosmology. And what this does is it models our supernova a lot better. There's a lot of stuff in our simulations that we're able to reproduce from the data that we weren't before. But needless to say, there is still some work that needs to be done. And this was a lot. And we'll see how we did. Good?
So yeah, there was a question on the, okay. There was a question on Zoom on what is on the x-axis.
Yeah, but then I saw them on the top,
okay,
actually.
So we have described the intrinsic color distribution of the supernova as a Gaussian distribution. So this is the mean of the intrinsic supernova color and the standard deviation. Then we've also gone and described the RV distributions of the galaxies with a Gaussian. So this is the mean RV of low mass galaxies and the standard deviation for low mass galaxies. Same here for high mass. And then the columnar reddening, the E of B minus V for low mass, low redshift, high mass, low redshift, low mass, high redshift, high mass, high redshift. And then finally, an extra parameter that is the intrinsic difference in luminosity as a function of the supernova color.
So there is a, okay. Can you try to maybe a good question? Can you put, okay, no, maybe I will take the question from Zoom directly at the end. But so there's a question by Dimitri saying how many known 1A SN are in the sample of 1,600?
So depends what you mean by known. There's only about 200 with spectroscopic confirmation. I believe in 2 or 3 slides, we're going to get to the overview of how many are likely 1A with the photometric classifier we use to identify them. Okay, so classification is what's coming up next. So this is the analysis, and it seems like there's a lot of questions on the classification aspect, so I'll take a little bit more time to talk about that. And so we've got our classification. We've updated our light curve fitter pretty significantly, and then we're going to talk about our distance measurements and corrections. Okay, so as promised, I'm going to talk about this first before I get to the other things, but we used 3 different classifying methods, and we made sure to compare them all. So we have Supernova, which is done by Anais, and that is a very fancy neural network sort of classifier that provides real-time classification of whether or not this is a type 1a, all based off of your 4 light curves. Worth pointing out that all of these classifiers are trained on simulated supernova and simulated core collapse. Then we went and tested them against our confirmed spectroscopic sample, which is only about 200, but I've gone and done this for other surveys. And we have SCONE, and we also used a random forest algorithm called SNRF. And then we have these 2 Venn diagrams that show all of the agreement of all of the different surveys. So according to all of the surveys, there's about 5% non-1A classification, or sorry, not surveys. All of the classifiers agree on about 5% non-1A contamination. So to answer your question, about 5% of them are likely not 1A, and we are fairly confident about the rest. As it turns out, the distribution, as you can kind of see, is not really expected to be centered around 50. It either picks up a relatively high confidence or a relatively high confidence of being a 1A either way. Are there any other questions? Right. So, with that,
So just,
of course.
but the type 2 supernovae, you can sort of reliably simulate the atmosphere and all of that, but you said those light curves were simulated.
Yes, sorry,
to
I was not terribly clear.
Type 1 were from the data.
So these, when I say simulated, I don't mean that we like do a hydrodynamic simulation. I mean that we have a collection of SEDs from other surveys of like, we've taken a type 108, type 1b supernova that happened in the sky, got its spectra over time, and then you can mangle that a little bit, move it around, and that's what I mean by simulate. So it's all based on SEDs that we've observed elsewhere.
Oh, okay.
Yeah, sorry, we don't have the power to do the full hydrodynamic simulations at the moment. So that being said, as a short reminder, our type 1A supernova need to be corrected for stretch and color. Stretch is how long it takes the light curve to decay. Color is again related to the flux between the 2 bands. And so our goal with using these simulations is to sort of try to correct for selection effects and biases. As you can imagine, for instance, if you have a distribution of supernova colors out in the universe, by the time it reaches you, you should expect it to be a bit redder, or yeah, a bit redder due to, you know, reddening from dust, for instance. And we're, for the first time, trying to sort of use our astrophysical intuition for this. And by that, we are including this effects of dust, as I showed before. And Phil Wiseman here did a lot of work on sort of getting a good estimate of the delay time distribution, which is to say we can look at the star formation rate of a galaxy and tie that to the likelihood of a progenitor, whether or not it's 2 white dwarfs or a white dwarf and something else. And we've taken that, put that into our galaxies in our simulations, pushed that all the way to cosmology, and we're going to try to use that to correct for any biases that we see in the data. And as it turns out, there are some weird things. So, one of the sort of fundamental assumptions of type 1A supernova is that you can correct and then they become standard candles. This is only technically true because, as it turns out, our galaxies and the host galaxies have a very clear and definitive impact on our type 1A supernova. So we have the supernova color here. Again, that's one of the things that we standardize with. and we have our distance residuals. And you can see that between the bluer hosts, the host galaxies, and the redder hosts, there is a very clear difference between the distances we measure in supernova and red hosts and the distances we measure in supernova and blue hosts. Now, the comforting thing is this is one of the first times that we've actually managed to capture this behavior in simulations. So that's great. We are starting to get a bit closer. And then you can sort of, this should be animated. There we go. So if you look here, you have the galaxy color, not the supernova color. And for blue supernova, the distance residuals match really well. But for red supernova, something's changed, and all of a sudden, our sample is entirely inconsistent. And that comes back to this, which is pointing at that there is some process happening with our supernova that is entirely driven by the host galaxy environments, and that seems to affect our redder supernova, our dimmer supernova, our more dusty supernova, perhaps, preferentially. And worth pointing out that this and our ability to correct for this is only about 2 years old. Every single supernova survey before has not really had a good explanation as to why this is happening. And we're still working on the explanation, but we've gotten a lot further.
So what is the explanation?
Okay, it depends who you ask, but as it turns out, it seems that if you look here, this is a good example of it. Basically, everything from here on is driven by differing dust distributions in the host galaxies. And that's why it gets wider a little bit with the increasing color as the reddening impact increases. Now, down here, this is pointing towards, because we expect these to be relatively dust-free, this seems to be pointing towards some kind of progenitor effect. Unfortunately, the ability to constrain that requires a lot more statistics at low redshift, something that DES alone does not have. But another survey that is being run here in France does have, namely ZTF.
Where do the lines come from?
The lines are our simulations. Yes, so while we may not entirely understand what's going on here in the data, our simulations are doing a very good job of recreating this. So up until 2 years ago, the simulation line would have been like that, and it would have had no extra, it's just been flat for both of them.
The cluster for the galaxy color points and what kind of graph, does that come from multiple different instruments as well?
No, this is all DES data. Mm-hmm. We have seen this in other surveys as well. So this is not just DES. This exists in SDSS and PanSTARRS, probably SNLS too if we had the statistics. But the point is, we are seeing this independent of the survey. But I figure to make the most convincing case, why not use a single telescope? Make sure it's not some sort of calibration issue. And I didn't really know where else to put this one. Patrick Armstrong and Ryan Camilleri are 2 graduate students in Australia, and they did a boatload of work on the pipeline stuff. Like, it's one of those things where it's really hard to show a graphic for the fact that these 2 are responsible, that our pipeline works and we got back our input stuff, but we did. It's because of them. I thought it would be nice to give them a little shout out here because, you know, not everything we do is immediately obvious, but this just would not have been done without them. And I think it's important to acknowledge that. So all of that leads to this. This is our Hubble diagram. So again, it's our redshift versus our distance. We have the low Z plus foundation sample. The low Z is about 5 different surveys over the course of 20 years. Foundation is 1 survey, and altogether that gives us about 290 supernova at low redshift compared to our 1,650 supernova at high redshift. And as promised, you can see over here, these are our likely non-1A supernova. Not only are they, you know, classified as such, but they live up here with a higher distance modulus, which means intrinsically dimmer. And we don't actually throw these out. We weigh every supernova by its probability of being a type 1A, and propagate that probability while we do our cosmological fit. So we do keep all of our non-1A supernova. We can't throw them out just because they don't agree with our data, but we do take care to make sure that they're weighed appropriately. And we have our residuals to our cosmological fit. Maybe this is a better example that all of our non-1A supernova are intrinsically fainter here. And overall, pretty good.
There's a bunch of non-1A underneath the dark blue as well.
Mm-hmm. We can't guarantee they're all, if we were selecting just based on this, that would be a bit of an issue, which is why we keep all of them, and they're still weighted. Even if they agree with our data, they're down weighted. And another good way we check is we go and we simulate all of our non-1A supernova and propagate them through. And if we see similar behavior in our simulated version of this, then we can be pretty sure that our contamination is comparable. So we can't remove it, but we can make sure we've got a good handle on it. So just a very quick kind of comparison. This was the DES 3-year results. As you can see, a lot smaller in every case. And what happens to the error budget? So our statistical uncertainty on W was 0.042, and our systematic was similarly large. That's about 4% in W. And we have, pretty significantly decreased that. I believe the next slide, I get into the systematics a lot more, so I won't answer any questions there. But our increased statistical power comes from having more. Any further increase or further decreases to these statistics is going to require a larger low redshift sample. But we've significantly improved this, and we've gotten a lot more systematic improvements as well. All right, here it is. There's a lot. So maybe that should be comforting to some people that we have a lot of uncertainties. We're certainly not forgetting any, I hope. And I'm going to kind of point out what the most important ones are as we go through this. So the good news is that non-1A contamination accounts for about less than 10% of the total systematic uncertainty. So this is comparing all of our different training samples we used for all of our different classifiers, as well as just dropping the simulated supernova all entirely and using a Taylor expansion to go off the expected cosmology. And it's, as you can see in this green thing, a fairly small concern, and that's good. Maybe there's still more work to be done, but this is absolutely not the showstopper that we were worried about. It's not even our biggest issue. So I got a lot of questions at Claremont when I mentioned this, when I said that calibration is not our largest issue. Calibration is still a big concern and something that we've got to work on, but every single one of these things circled here is somehow related to our knowledge of the astrophysics behind our supernova explosions. And these account for about 35% of our total systematic uncertainty budget, which that is a showstopper. You're not going to be able to do kind of next level cosmology with that amount of systematic uncertainty there. So we need to figure this out. Unfortunately, DES alone does not really have the statistics for redshift range. Yes?
I just want to understand what you just said. You're not going to be able to do that. You're talking about future experiments.
Yes.
Okay.
So if we want to figure out whether or not dark energy evolves with cosmic time, we're going to have to add another parameter, which means you need more statistics and you need to be more precise to break that signal between regular dark energy or dark energy that evolves with time. And
so you're essentially saying that like LSST had error bars the size of the orange or the yellow button.
Yeah. And I actually show that in the W0 space. But yeah, exactly.
So exactly are these uncertainties that are really big?
Okay.
That looks like alpha, beta, and gamma evolution are the big ones.
That might be, yeah, that's part of it. So they're all unfortunately very complicatedly related. So the way that we measure distance is that every supernova has a peak brightness, a stretch, and a color. And then the entire sample, when you fit cosmology, they all have an alpha. The entire sample has a single alpha, a single beta, and a single gamma. And so alpha relates to how, it's a nuisance parameter that kind of describes how the stretch of the supernova relates to the intrinsic brightness. So for instance, if it was 0, you would need no standardization at all because the stretch would not be related to the brightness at all. The problem is there's a lot of information buried in alpha and beta and gamma. I can point to beta as a bit more obvious in a connection, where this beta parameter for supernova really strongly correlates with the RV of the host galaxy. So if you look at your beta and how that changes with the mass of the host galaxy of the supernova, that maps really well to the expected RV you should see. So there's some astrophysics going on here. Is that?
So these are sort of fitting parameters of the light curve correction.
Yeah, except sort of related to the global sample.
And then for these, the sort of statistical uncertainties and the fit, because I guess you do the fit to minimize the dispersion.
Yes, yeah, they exist to minimize the dispersion. Exactly.
So in that sense, it would be a little statistical, right?
Yeah, it's all a little statistical. Yes, these are statistically inferred, but for instance, we can make improvements. So up until 2 years ago, we knew that this beta parameter evolved with mass, but all of our simulations just had a flat beta. And in fact, we go way back. Sorry, this is the stuff that really I get excited about, but like that beta describes the slope of this line here and then gets muddled out by this RV. But you'd expect that if I, measured the slope of this line, it would match what our beta value is. But yes, a lot of statistical inferences buried in there. And since beta is for instance, beta and gamma are strongly related to the dust populations that we put in. So while technically these are considered separately when we propagate them forward, they all come back to what's happening behind the scenes with the explosion physics and what's in the host galaxy and all that good stuff. So that brings us to our cosmological results. And so all of these plots I'm going to show have the full statistical and systematic uncertainties included. We have our matter density versus our dark energy density of the universe for the DES 5-year results alone, and then we are adding more and more extra probes. So this one is perhaps not too shocking that we live in an accelerating universe. We've been pretty clear on that one. We are also pretty consistent with a flat universe, exactly on the money here. And this is flat lambda CDM. This is, without flat lambda CDM. And this omega matter is a little, yes.
So the uncertainties you quote are 1 sigma, the standard ones.
It's standard 1 sigma uncertainties, and this omega matter is a little higher than normal. And that was one of the sort of the first interesting signs, and it's going to get a bit more interesting, like I said, dark energy. It's going to get a bit more interesting when we start combining with our other probes. So this color scheme will show up in the future. DES alone, supernova alone is blue. Our final results with all the other probes is red. Flat universe, a bit more normal omega matter values. So now we're going to talk about W. The astute amongst you may notice that that is distinctly not really -1. And so from supernova alone, well, it's within 1.25 sigma for W. However, when we include our other probes, we're not getting a cosmological constant. So Admittedly, this is not like a crazy offset from ΛCDM. We're only about 2.2 sigma away, but it is very interesting to note that a separate cosmological survey, the Union sample, which only has about 400 of 2,000 supernova shared with an entirely different analysis structure, came out and found a similarly discrepant W value. So we're starting to see hints in supernova of other independent conformations that we might not have a cosmological constant. Of course, this could be something else, and we'll kind of briefly touch upon that, but interesting considering the last big cosmological analysis with type 1a supernova, which was Pantheon Plus, came out with a very strong W -1.
Which of these are the pictures on the right?
Yes. So this value,
That is the red.
that is this red one here. Yeah, it's not too far off. It's just a little off, but normally it's here. And then the dark blue more accurately corresponds to this light blue banana. Yes. Then, as you asked, if we split up W instead to a dark energy equation of state that's independent of redshift, plus one that evolves with redshift, we get this. And so this is why we're going to need extra statistics and increased understanding of our systematic uncertainty for LST, because switching to this increases our constraints a lot, or decreases in constraints. We need better constraints because we have more data to probe. And so, unfortunately, right now, we're not really getting a lot of stuff that's terribly convincing either way. You can see the uncertainties on W0 and WA for supernova alone in blue, and with our other probes in red. It's still kind of hard to say whether or not we're definitively seeing something. This means that we still have a lot of work to do for LSST and Nancy Grace Roman, but I think the more interesting thing I find here is that we are sort of coming to the edge of wondering whether or not supernova are really compatible with our other distance measurements. We are just kind of barely brushing up against them now, and that could be a little worrying, but we need more supernova data to really be able to say that with confidence. However, we also do some Bayesian evidence to kind of check what our most favored model is. And right now, it is still our flat wCDM, at least for the moment. So that is what DES has done. The papers are split into two. We have the actual cosmological results, and then where all of the analysis was done. And they're very interesting. I would recommend everyone take a look. But very quickly, as we wrap up towards the end here, if you have any questions before I talk about kind of what supernova needs to do next, now would be a good time. All right. So what's next is obviously a very good question. The Legacy Survey of Space and Time and Nancy Grace Roman will not be presenting data for the next 4 years if you're particularly optimistic. If we want to constrain that W0 WA and the evolution of dark energy with cosmic time, we are going to need sub% precision on W, which we just don't have right now. Good news is that non-1A contamination is, to first order, a solved problem at our high redshifts. Can we do better? Yes. Is it less than 10% of the total uncertainty? Yes, I think we can put our energy towards other things right now. The DES sample is pretty dang good and pretty well characterized, all coming from a single telescope that has been extremely well studied. And we have a slight discrepancy with ΛCDM at 2 sigma. And so that leaves kind of what are the extant things that we can fix. Obviously, our statistics will get better with Roman and an LSST, but the 3 big things that stick out to me that we need to work on are astrophysics, 35% of our error budget, calibration, which is always like 15, at least 15%, and that low redshift sample. So, you know, obviously, what might you want to do is, well, we're sitting on ZTF. So ZTF, which is still taking data, today has about 3,500 spectroscopically confirmed type 1a supernova. That's ridiculous. That is single-handedly double the size of DES, which is our largest one right now. So obviously, there's a lot of great work to be done by including ZTF. And here is an example of what that looks like. We have the real DES data, some decent simulations of ZTF. I still need to do some work on those, and as well as the Hypersupreme CAM and SNLS 5-year samples up here to give us some extra range at the high redshift range. So the big thing with this one is that adding ZTF is going to solve our issues with only, 200, 300 supernova at low redshift. Immediately, that'll increase our precision on W by about 40%. Even if we fixed no issues at all, that's fantastic. And that can be done before LSST, that can be done before Roman. And if you want to do better than that, which I do, ZTF is a single telescope that is all sky. Nominally, the selection effects are significantly easier to calculate than our historical low redshift sample, which had one of the filters degrade and then break during observation, and then they just replaced it with a different filter, and we still use those supernova today, which is kind of rough, but we're just right now really need those low redshift statistics. So that simpler selection effect combined with this really hefty amount of statistics and a huge redshift range is going to provide a lot of really good data to probe to get a better handle on those astrophysics. And kind of the broad idea is we want to be able to separate our intrinsic progenitor effects, like what causes the supernova, because we should expect to be able to track that with the star formation history of our galaxies and with redshift, and separate that out from the dust, which should have a different redshift evolution. And with this amount of statistics, it should be a lot easier to extricate those two. So that's actually the final slide. We've got a lot of work left to do, but I think we can do it. And most excitingly, we can do all of this stuff now, today, before LSST comes out. And this will be the best supernova sample in the pre-LSST era, and probably the best supernova sample till at least 2030, when this gets put together. That's it.
Questions from the room?
Is there a significant overlap between the supernova sample at low redshift and the CPI?
Oh yeah, that's a good question. Significant compared to these numbers? No, not really. The ZTF will be pretty helpful in, actually, no, sorry. So the problem with the Cepheid anchor measurement is those are really time limited. So we may get a couple more from ZTF, but unfortunately, the historical sample that has been used in the shoes analysis is fairly set in stone because the measurements of those supernova are gone, they're done. We can't change them. If you have a lot of patience and ZTF is going, we might get a couple more in Cepheid hosting galaxies, which will improve our constraints a little bit. But in ZTF, we're starting to look towards like strongly lensed supernova as a measure of H0. And kind of, it should provide us the ability to use an independent of Cepheid's measurement.
There was a question by Simona on Zoom. She was waiting for Simona. Can you turn on your sound?
Yeah, thank you. Can you hear me?
Yes.
Yeah.
Hello.
Yeah. Hi. So I have a question. What strikes me the most of these DES supernova results is the marginality of the intersection of the probability curves with the other probes. So, for example, if you have CMB, BAO, a 3+2 point, they all have values of omega matter W0 and WA more or less in the same region. Yeah, exactly. And is the figure 8 of the paper is even more dramatic if you look at W0 omega matter plots, right? So this looks like something at within 2 sigma, but kind of at the margin of the 2 sigma. Do you have any comment on that?
Yeah, well, one, I obviously find that one a little bit worrying as well. So the thing that I think is causing this is our low redshift sample. So, you know, hold on, sorry, that is a tricky question. Basically, all we're doing is trying to measure the change in distance with redshift. And if we have a significantly different low redshift sample, that's got the possibility to mess up our derivations a decent amount, which then could be causing this discrepancy that we're seeing. This is another problem I think will absolutely be addressed with ZTF. If it's still there, then I think it's definitely real cosmology. If it's gone, then it was definitely our low redshift sample. But that other measurement I pointed to the Union paper by Dave Rubin, they use the same low redshift anchor sample. And I don't think it's a coincidence that they're saying the same kind of like barely overlapping contours. Overall, I don't know. I kind of hope it's real. That would certainly be a lot more fun and we'd see a lot new physics. But I unfortunately do think this is a low redshift anchor sample issue.
Okay, makes sense actually. Thank you.
Mm-hmm.
Yeah, I don't have a feel for how far away, how hard would it be to just get rid of the low redshift sample completely and look at the curvature and those curves at higher redshift? You should be able to see.
So actually, I love this kind of question. I always get one question that feels like I planted somebody in the audience. Thank you. So I actually did that. I went and I put together the SDSS photometric samples and the Pan-STARRS photometric samples and did a full cosmology analysis with them without any low redshift anchoring. As it turns out, we can do it, but it's not great.
But I mean, there's got to be some limit to the number we can get at a low redshift. At a high redshift, that's got to be easier. Mm-hmm. So in 20 years, will it be better just to use high redshift?
Honestly, in 20 years, unless something changes, I think we'll still be using ZTF. I referenced that this is, first of all, we're not done taking data. Second of all, this is only the spectroscopically confirmed. If we did phototyping with ZTF, which is something I'm working on, this will go up to 30,000. And, you know, maybe I'm saying the wrong thing that I can't imagine us needing more than 30,000 low redshift supernova, but I can't imagine us needing more than 30,000 low redshift supernova.
Almost seems like there's sort of a bald spot between us if one is going very deep, that not so many objects, and is it possible to sort of get a lot more intermediate and do what Ken was suggesting this way?
Yeah, if you could put in SDSS and Pan-STARRS right here, and that covers up the bald spot pretty well. The thing is, unfortunately, like right here, or fortunately, I should say, right here is the least important kind of redshift range, because this is shown in log space, but you know, in log space, it doesn't really matter unless you have some really strange cosmology that causes a dip in this bald spot. Your best constraints are going to be down here and up here. But the short answer is SDSS and Pan-STARRS, we have the data that goes in right here, and that could be put in and covered up that bald spot.
Oh, I see. But to get the really low stuff, the volume is minuscule, so it would. What's the limitation that we just need to take a very long time or to fill that in?
Mm-hmm. Exactly. That takes time.
Yes. Yes, how LSST will change the data
So it'll force us to change the analysis. It's actually not going to change the data all that much. There's a reason I kept making allusions to the Nancy Grace Roman Space Telescope. LSST is primarily going to live here. You may notice there's a lot of supernova here. So unfortunately, it's not going to really shake up the redshift range, but the amount of data we're expecting is definitely going to force us to rethink our approach to how we do all of these bias corrections and stuff. The thing that really excites me is Nancy Grace Roman, which is open source. The data will be available immediately, and that's going to actually start living up here. And that'll really change our data quite a bit.
I have a question outside the field. Can you comment on exactly the open data and data sharing for all these experiments?
Right. That's a lot of politics. I honestly have no idea what it is for LSST. I assume everybody here is part of LSST. I imagine. I don't know what it is for LSST. I know that DES is finished and the actual data should be out in a couple months, certainly by the end of 2024. That'll all be free and open. The ZTF DR2 is coming out soon. They will not be cosmology ready, but it'll be a great opportunity to get a good start on preparing, because you'll have all of the data, but there's some calibration issues that need to be solved.
When you say the data will be public, what level of data?
I believe the discussion is still ongoing for DES. Certainly the covariance matrix and all of the distances. I also believe all of the light curves as well. And so, yeah, so DES, summer this year, all will be public. ZTF, not cosmology ready, but still pretty darn good, will all be public about summer this year. And then we expect the cosmology sample to be out late this year, early next year, give or take. Yeah.
I have another question from the chat on Zoom. Can you comment on the H0 problem?
I think it's physics. New physics. Right. So in 2018, there was a conference that talked about the H0 tension, and a lot of potential systematics on the Cepheid side were discussed, proposed, things like preferentially selecting galaxies with a high star formation rate, other things like, you know, a bunch of selection effects that could affect and bias our H0. In the 2022 SHOES analysis, all of these suggestions, specifically and most importantly, that star formation selection effect, were tested and make no real impact on our H0. I have not seen any convincing arguments that this is a Cepheid or supernova selection problem, which makes me believe that it's going to be some kind of new physics, but at risk of plugging ZTF too much. With ZTF, we have a couple of super strongly lensed supernova, which do provide an alternative measurement of H0 between the original and the lensed image. Comparing those two distances in time will give you an estimate of H0 independent of Cepheids. And so that'll be a great way of testing out whether or not we see the same thing, the same H0 tension. Also, gravitational waves, when we get a couple more bright sirens, will be a very good estimate as well.
Thank you very much. Other questions to the speaker? Okay, if not, I think we can stop here. Thank you very much. And we can keep chatting the coffee. Thanks.